Okay, now we come to the second part of our lecture, that is K nearest neighbor algorithm. K nearest neighbor algorithm is arguably the simplest machine learning algorithm that is building the K nearest neighbor model consists of storing the training data. To make a prediction for a new data, the algorithm finds the closest points in the training set. Uh, the k-nearest neighbor algorithm is also called as instance-based learning or lazy learning. Uh, then we come to the detail of the nearest neighbor algorithm, k-nearest neighbor classification. In its simplest version, k-nearest neighbor algorithm only considers exactly one nearest neighbor, which is the closest training data point to the point where we want to make a prediction for. The prediction is simply the known data or known output of the training point. Here we briefly describe the overall part of the algorithm, the basic k nearest neighbor algorithm for classification. We have the training method, we have the training data set, and we save the training examples in the training method. At the prediction time, what we find the k training examples for k training examples x1 y1 to xk yk that are closest to the test point test example x. For a test example x, we find that it is closest to which training example. And at the prediction or the classification of the x, we predict the most frequent class among those output and those and out it and from those output and make it as output for x. For the regression problem, we predict the average among the y, average among the outputs for for input test example x. We make it. So we elaborate this algorithm in detail, and then it will make the understanding what it means. So this is overall, this is just a description of the algorithm. So here I run this part of the code, and we will see that here we are using again the synthetic data set, and but here at this time we have put three test points for this data set, the as represented as a star. We added three new data points shown as stars. For each of them, we mark the closest point in the training set. The prediction of the one nearest neighbor algorithm is the label of that point. For example, this test point is closest to the this point, so we assign this test point the same label as belong to this class. And similarly, this test point is closest to this in this instance, this example, so we assign the same label for this class to this class. And likewise, for this test point, it is close to the training class 0, so we assign this test point the same class, the same label as class 0. So this is the example of one nearest neighbor classification. So instead of considering only the closest neighbor, we can also consider an arbitrary number k of neighbors. This is where the name of the k nearest neighbor. So instead of one neighbor, we use more than one neighbor. When considering more than one neighbor, we use voting to assign a label. This means that for each test point, we count how many neighbors belong to class 0 and how many neighbors belong to class 1. We then assign the class that is more frequent. In other words, the majority class among the k nearest neighbor. The following example is using the three closest neighbors. So we again discuss this above example, but now this time we consider the k is equal to 3 or 3 nearest neighbor and find that what is the output. So now for this test point, we compute its distance to the three nearest neighbor this one, and this one. And among these three neighbors, two neighbors belong to the class 1. So now at this time, we assign this test point uh, to the label 1 instead of label 0. And likewise, for this test point, we consider its distance from these three labels, and we find that since two instances belong to the class 1, so we assign it as a label class 1. And for this test point, we compute its distance to nearest three nearest neighbors and find that these three nearest neighbors belong to the class 1, belong to the class 0. So we also make this label as a class 0, label for this test point as 0. So again, the prediction is shown as the color of the class. We can see that the prediction for the new data point at the top left is not the same as the prediction we used with one nearest neighbor. So here in this point, this test point was belong to the class 0, but now three nearest neighbor, using three nearest neighbor, it belongs to the class 1. So now let's look at how we can apply the k nearest neighbor algorithm using the scikit-learn. And while this illustration is a binary classification problem, this method can be extended to a dataset with any number of classes. For classes, we count how many neighbors belong to each class and again predict the most common class. So now let's look at how we can apply the k nearest neighbor algorithm using the scikit-learn. And here, first we split our data into training and test set so we can generalize the performance. So we split the data into training set and the test set. So here it is doing this. So we are making actually the synthetic data set and splitting it into training and test set. And then next we import and instantiate the class. This is when we can set parameters like the number of neighbors to see. Here we set it to 3. So we use the 3 nearest neighbor classifier. So we are using the 3 nearest neighbor classifier. So we are importing this classifier from the sklearn library. So now we fit the classifier using the training set. For k neighbor classifier, this means storing the data set so we can compute the neighbors during the prediction. So this is the training set and this is the corresponding test set. This is X train and Y train. This is the training input data and these are the predictions, and we apply the k nearest neighbor on the training data. And then to make the predictions on the test data, we call the prediction methods. For each data point in the test set, this computes its nearest neighbor in the training set and finds the most common class among those. So this computes the test or the prediction for the test set. For the test set, we have only the attributes or features. We don't have the prediction, and the algorithm will find the prediction. So we make the prediction for the test set, and this makes the prediction. To evaluate how well our model generalizes, we can call the score method with the test data together with the test labels. So we have the test labels and we have the prediction labels, and we find that what is the test label and the prediction labels, and by them we find the accuracy. So here it finds that the accuracy is 86%. So we see that our model is about 86% accurate, meaning the model predicted the class correctly for 86% of the samples in the training set. That's good enough. Analyzing the k neighbors classifier. Now we analyze the k nearest neighbor and its boundary. For two-dimensional dataset, we can also illustrate the prediction for all possible test points in XY plane. We color the plane according to the class that would be assigned to a point in this region. This lets us view the decision boundary, which is divide between where the algorithm assigns class 0 versus where it assigns class 1. Following code produces the illustration of the decision boundary for 1, 3, or 9 neighbors. This code will generate the boundary of the k nearest neighbor for n is k is equal to 1, 3, and 9. So here it is the result, and it shows the when k is equal to 1, or decision basis on the only one neighbor, decision is made considering the 3 neighbors, decision is made considering the 25 neighbors. So we can see that on the left figure, using a single neighbor results in decision boundary that follows the training data closely. This here the decision boundary, it exactly follows the training data. And considering the more and more neighbors leads to a smoother decision boundary. When we increase the k on the neighbors, the boundary becomes smoother. Here it is the very abrupt, and there is difficult to represent this boundary, but here the boundary becomes smoother and smoother. And in other words, using the fewer k corresponds to high model complexity. Here the model complexity is high because it is very difficult to represent these this shape, this representation. And using many neighbors corresponds to low model complexity. When we use the too many neighbors, the model complexity is too low. If we consider the extreme case where the number of neighbors is the number of all data points in the training set, each test point would have exactly the same neighbors, and all predictions would be the same. This is that most frequent class, it will come up from the training set. So here we can see that for this, when k is equal to 25 or 25 nearest neighbor, then we can see that we can represent this boundary is simple, and we can represent it by a 4 piecewise line. For example, we can represent this boundary line 1, then line 2, line 3, and line 4. But here it is a little difficult to represent this boundary, because so many piecewise lines, and here it is too difficult because it is a combination of many lines, so it is very complex. So we have to make a, but here the performance is it is too noisy. Here the performance is acceptable because some of the points are misclassified, but here the many points are misclassified. So it is a compromise that what we should keep the value of k. So here are some general rules. Small value of k or neighbors captures the more fine structures of the problem space better. It captures the fine structures in the problem space when small k is equal to k is smaller. It may be good for training set, and but for larger k, less sensitive to noise. Larger k is less sensitive to noise and better estimates the discrete classes. But larger training set allows the use of larger k. When we use the larger k, when our training set is large enough. So let's investigate the connection between the model complexity and generalization. We investigate model complexity and generalization. We will do this on the real world breast cancer dataset. We begin by separating the dataset into training and test set. Then we evaluate training and test set performance with different number of neighbors. The results are shown in figure. So here we import the data from the sklearn dataset, load breast cancer, and these are the details and uh, data, and here take the data and separate it into training and test set. And this is the training set accuracy matrix, test set accuracy matrix, and training settings. And then we use our this classifier and k-nearest neighbor classifier, and then we use that neighbor setting. We make the setting for a different number of neighbors. Value of k, we vary the value of k and check the accuracy of the test training set and the test set. So here it is the plot, and we see that as we increase the k nearest neighbor from 1 to 10, the training set accuracy, it drops down. Means the training set accuracy is highest at when k is equal to 1, then it gradually drops down and it becomes smooth, um, up to 10 or so. But for the test set, when we increase, and initially the k is equal to 1, when we change it to 2, it abruptly uh, drops down the accuracy, and then it begins to increase, and after some time, after the some values of k, it begins to settle down. So the plot shows the training and test set accuracy on the y-axis against the set of n neighbors on the x-axis. We can see some of the characteristics of overfitting and underfitting in the model. What is the overfitting? That it kept it the model performs well on the training set but performs poor on the test set. And what is the underfitting? That the model performs poor on the training set as well as poor on the test set. Considering a single nearest neighbor, the prediction on the training set is perfect. When k is 1, the prediction on the training set is perfect. But when more neighbors are considered, the model becomes simple and the training accuracy drops. The test accuracy for using a single neighbor is lower. For a single neighbor, the test set accuracy is lower. And then using more neighbors, uh, that using the single neighbor leads to a model that is too complex. This is because of overfitting model performs well on the training set and has no generalization or does not perform well on the test set. On the other hand, when considering 10 neighbors, the model is too simple and performance is even worse. So when n is too high, then the model is too simple that it does not model the captures the properties of the function, or it does not perform well. The best performance is somewhere middle using around 6 neighbors. So best performance is about somewhere about neighbors are k is equal to 6 neighbors. The performance is highest, and still it is good to keep the scale of the plot in mind. The worst performance around 88 is around 88% accuracy, which might be still acceptable for some applications. The worst performance is 88% here in this case. So this is our k nearest neighbor works on the basis of distance, Euclidean distance. So, but in some applications, the distance may be the weighted distance, and when we want to suppress some features, and when we want to boost up some features, so this is the then we use the weighted Euclidean distance for the k nearest neighbor. So this was about the application of the k nearest neighbor for the classification problem. In the subsequent part of this lecture, we will discuss the k nearest neighbor for regression problem. Thank you.